Have you ever just stopped and looked around at everything? The screen you're looking at right now, the air you're breathing, even you. It's all made of the same basic stuff. But what is that stuff? You know, for most of human history, that was a total mystery. Well, in this explainer, we're going to unravel that mystery. We're going to follow the breadcrumbs that led scientists to finally crack the code of the atom.
So what is everything made of? I mean, that's the big question, right? It's something people have been wondering about for thousands of years. If you could just keep breaking things down, smaller and smaller and smaller, what would you eventually find? The short answer is the atom. But trust me, the story of how we figured that out, it's absolutely incredible.
Okay, so our journey starts way, way back. We're talking over 2,000 years ago in ancient Greece. There's this philosopher, Democritus, and he has this really cool thought experiment. He says, imagine you take something, anything, and you cut it in half. Then you cut that half in half, and you just keep going. Eventually, he thought, you'd have to get to a piece so tiny that you just couldn't cut it anymore. He called this tiny theoretical particle atomos, which literally means uncuttable. What a brilliant idea, right? But here's the catch, there was no way to prove it. So for the next 2,000 years, it was just an idea.
All right, let's fast forward a couple of millennia to the 1800s. This is where things really start to pick up steam. And this timeline right here, this is basically our roadmap for the rest of this journey. As you can see, our picture of the atom didn't just pop into existence fully formed. Oh no, it was this wild ride of building a model, smashing it to pieces with a new discovery, and then rebuilding it all over again. It was one of the most exciting times in the history of science, and we're going to walk through every single one of these major shifts.
So, how do you take something like atomos, this cool philosophical idea, and turn it into actual science? Well, that's where our very first scientific model of the atom comes in. This is the moment it becomes a testable theory.
Okay, so in 1803, you've got this English chemist, John Dalton, and he's messing around with chemical reactions, and he notices something really, really important. He sees that different elements always seem to combine in these perfect, predictable ratios. And he's thinking, how is that possible? The only way it makes sense, he figures, is if all matter is made up of these tiny, solid, indivisible spheres, kind of like microscopic billiard balls. And just like that, this wasn't just philosophy anymore. This was a real scientific theory that actually explained real-world data. Dalton basically put the atom on the map for chemistry. Dalton's uncuttable billiard ball, it was a massive step forward. But it turns out that whole uncuttable part, well, that wasn't quite right. The next big discovery was about to crack the atom wide open. So now we jump to the end of the 19th century. A guy named J.J. Thomson is doing these experiments with vacuum tubes. He passes an electric current through one and poof, this mysterious beam appears. They called it a cathode ray. So Thomson starts playing around, using magnets to bend the beam, and he realizes this beam is made of tiny particles, and these particles are negatively charged, and they're thousands of times lighter than even the smallest known atom. He had just discovered the electron, and in that moment he proved that atoms weren't uncuttable at all. They had smaller parts inside them.
Okay, so this created a new puzzle. If atoms have these tiny negative electrons inside, but we know atoms are neutral overall, where's the positive charge hiding? Thomson came up with what he called the plum pudding model. Just picture it. You've got this big fuzzy ball of positive pudding, and then you have the negative electrons just sort of dotted throughout, like plums or raisins. It was the very first attempt to actually map out the inside of an atom. A pretty good first guess, but this picture wasn't going to stick around for long.
Yeah, that plum pudding model, it was about to be completely blown apart. And kind of ironically, it was by one of Thomson's own students, a guy named Ernest Rutherford. His work would totally rewrite the book on the atom's structure.
You see, Rutherford's experiment was actually supposed to prove the plum pudding model was right, but the result he got was so bizarre, so completely shocking, that he later said it was, well, you can see the quote right there, it was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. I mean, can you imagine? It just completely shattered everything they thought they knew.
So here's what they did. It was actually pretty simple. Rutherford's team took these tiny, positively charged particles. Think of them like microscopic bullets called alpha particles, and they fired them at a super, super thin sheet of gold foil. Now, if the atom was this soft pudding, all those little bullets should have just zipped right through. And yeah, most of them did. But, and this is the mind-blowing part, every once in a while, about 1 in 8,000 times, one of them would bounce almost straight back.
The only possible explanation? All of the atom's positive charge and almost all of its mass had to be crammed into an impossibly tiny, dense core at the center. He called it the nucleus. The rest of the atom was almost entirely empty space.
So Rutherford gave us the nucleus. Awesome. But in doing so, he created a whole new puzzle. Okay, think about it. If you have this positive thing in the middle, the nucleus, and these negative electrons are orbiting it like planets, what stops them from just spiraling into the center? Basic physics says they should, and the whole atom should collapse.
Yeah, according to the physics at the time, an orbiting electron should be giving off energy, slowing down, and just, wham, spiraling into the nucleus. All matter should just collapse in on itself in a flash. But obviously, it doesn't. We're still here. So a physicist named Niels Bohr came up with a pretty radical solution. He said, what if electrons can only exist in very specific energy levels? Kind of like rungs on a ladder. They can jump from one rung to another, up or down, but they can never be in the space between the rungs. These orbits were quantized. They were stuck at set levels, which meant they couldn't spiral to their doom. It kept them stable.
Bohr's model was brilliant. It saved the atom from collapsing. But it still pictured electrons like these tiny little planets zipping around on perfect fixed tracks. The truth, as a guy named Erwin Schrödinger would show, is way, way stranger and a lot fuzzier. We're now officially stepping into the bizarre world of quantum mechanics.
So Schrödinger's model completely throws out the idea of these neat little orbits. Forget planets. Instead, it says that electrons act more like waves, and they exist in these regions of probability. We call them orbitals. So we can't ever know exactly where an electron is at any given moment. All we can know is the area where it's most likely to be. The atom isn't a tiny solar system anymore. It's this dense nucleus surrounded by these fuzzy probability clouds. And this, essentially, is the model we still use today.
Okay, so we've got a handle on the electron cloud. But for the last few minutes, we've kind of ignored the thing right at the heart of it all, that tiny, dense nucleus that Rutherford discovered. It's time to zoom way, way in and see what's actually going on in there. Just take a look at this. This is the breakdown of an atom's mass, and it's mind-boggling. That huge electron cloud we were just talking about, it makes up almost 0% of the mass. It's practically nothing. Over 99.9% of all the stuff in an atom is locked away in that impossibly tiny nucleus. Now, scientists knew it had positively charged protons in it, but when they added up the mass of the protons, it didn't add up. The numbers were wrong. There had to be something else in there with them.
And sure enough, in 1932, another one of Rutherford's students, James Chadwick, finally found the missing piece of the puzzle. It was the neutron. It had about the same mass as a proton, but, and this is key, it had no electric charge at all. And with that discovery, the basic picture was complete. You have protons and neutrons packed into the nucleus, and you have electrons buzzing around them in orbitals.
But wait, that just creates another problem, doesn't it? How on earth do you cram a bunch of positively charged protons together in a tiny space that should be repelling each other like crazy and just flying apart? Well, they're held together by the most powerful force we know of in the entire universe, the strong interaction, or the strong nuclear force. It's more than 100 times stronger than the electromagnetic force that's trying to blow them apart. The only catch is, it only works over incredibly tiny distances. It's like the universe's superglue, holding that nucleus together.
And just when you think we finally hit the bottom, that we've found the fundamental bits, physics goes and reveals another layer. It turns out protons and neutrons aren't the end of the line either. No, they are made of even smaller particles called quarks. If you look at this table, you can see how it works. A proton is 2 up quarks and 1 down quark, giving it that positive charge. A neutron is 1 up and 2 downs, making it neutral. As far as we know today, these quarks are the truly fundamental building blocks of matter.
So, after all that, why does this deep dive into the guts of an atom even matter? Well, because it explains pretty much everything. The way those outer electron clouds behave dictates the entirety of chemistry. Whether atoms decide to give away an electron, creating an ionic bond, or whether they decide to share electrons in a covalent bond, it's all driven by the weird quantum rules we just uncovered. This is literally how these fundamental particles build our entire world, from a grain of sand to a star.
So, what a journey, huh? We've gone from a simple, uncuttable sphere, all the way to a fuzzy, probabilistic cloud of electrons orbiting a nucleus made of protons and neutrons, which themselves are made of quarks. We've peeled back layer after layer of reality. But, every great answer in science just leads to an even better question. So here's the final thought. What's the next layer down? What, if anything, are quarks made of? Well, that's a question for the physicists of today and tomorrow to try and answer.